Really?
Right, we now move on to the section of the space course which is involved in discussing relativity and space and time and how it dilates and changes and all the weird stuff that happens when we approach the speed of light. But before we do this, we have to address this, which is called the luminiferous ether and the Mickelson and Morley experiment. Now, I think I spelled Mickelson wrong there, it doesn't matter. The pronunciation of Mickelson can be Mickelson or Michaelson, it doesn't matter. He was an immigrant and sometimes it was pronounced Michaelson by the Americans and so on. So I'm going to say Mickelson because that's the one that I grew up with in his name. Now, so what is the luminiferous? Now, luminiferous means light-bearing. Lumen meaning light, and as in the same word as Christophoro or Christopher, opher means to bear. So, Christopher means Christ-bearer. So luminiferous means light-bearing. So this is the luminiferous ether. Now, what is it? Well, to understand what the ether is, you have to understand where it came from. Now, I am going to say straight away, it doesn't exist. It's made up. Okay? So we have to understand why we believe this for so long. So let's have a think about what it is. The ether's history. It was first proposed by, I haven't even told you what it is yet, but it was first proposed all the way back in the time of Aristotle, when they had 5 elements, and the elements of earth, wind, fire, and something else. What was it? Water, that's it. And encompassing the whole lot, contained with, that kept it all together, was this mysterious substance called the ether. It enveloped all of time and space. It made all things work. It bound earth, wind, fire, and all that together. Okay? And it was this magical, mystical, spiritual thing. And because it was in the Greek writings, it was believed, like Aristotle's idea of, we have 5 senses. So that went down in history. A lot of people, if you ask them today, how many senses do you have? They'll say, oh, we've got 5. Well, that's rubbish. We don't have 5 senses. We've got more than 5 senses. We've got taste, touch, and all the other ones that we normally know, but we also have proprioception, which is I know exactly where my hands are without even seeing them. I can touch my nose even though I'm in a dark room. I also have stereo perception. I've got the ability to balance on things. So humans have got miles of other senses that we just do not consider. But we teach kids because it's nice to have the number 5. 5 fingers, 5 senses, kindergarten. Okay. And those 5 senses were delineated back around about 500 BC by Aristotle, and it kept on going down through time immemorial. So this idea of this mysterious ether has been around for thousands of years, until it came in the middle of the 1600s, mid-17th century, by a French philosopher by the name of René Descartes, from which we get the whole idea of the Cartesian numbering system. He was a mathematician as well as a philosopher, and he's the one who we have that I think, therefore I am. He's the one who understands that to be a conscious human being, I have to be able to think. So, cogito ergo sum, I think, therefore I am, is René Descartes' most famous statement. Okay, you can talk about René later on. But because remember, he was not just a philosopher, and in those days you weren't just a philosopher, you weren't this or that, you were a person who did a lot of things. He also was a mathematician, and he was also a physicist, even though we didn't have physics at that time. We called it basically naturalism. And he was wondering how things move. And the only way things could move is if one thing made another thing move and then made another thing move. So in other words, movement must be given to an object from one body to another. We would now call that work. But then he looked up in space and he saw that Saturn and Jupiter and Venus and the moon moved, but they weren't being pushed by anything. So his idea that if one object had to move by being pushed by something else, how could the planets be in motion if they're not being pushed? So he thought, oh, that's right, the ancient Greeks said there was this mysterious thing called the ether, and the ether exists everywhere, even in space, and therefore that caused motion or enabled motion to happen. So he then had this idea that all of space must be filled with a type of matter that we could not see, called the ether. By the way, the pronunciation of this is ether. That AE is a very old-fashioned lettering combination in both Greek and English, and it is English. Okay, so there are a few letters that have gone out of our language, and the AE is supposed to be joined together as one letter. So René Descartes then gave greater presence, made it more scientific to this concept of ether. Okay? The problem is, it's becoming scientific. And when something becomes scientific, it's going to be hard to shift. Then Isaac Newton happened. And as we know, Isaac Newton's the father of motion. He took up René Descartes' writings and used it, understood gravity and so on. And then he said, okay, the way that gravity moves is by, gravity must move through something. And he called it that there must be like a waterway. The way that you can influence one thing by another is by waves. And he called them ether waves. Then, the father of modern understanding of light, Augustin Jean Fresnel, he said that this ether must be what light travels through. And we can't see it. That's the reason why light can travel in space where there is no air. So even though we know that all waves need a medium, don't we? We all know that. That was from the beginning of our understanding of waves. Waves need a medium. You can't have sound without air. You can't have water waves without water. So you can't have light without a light wave medium. Does that make sense? It made sense. So we had to have this ether. This ether was this magnificent thing called, I'll show you how magnificent it is. Let's go and idealise what are the properties. And this is called the ether model of the transmission of light. The ether model of the transmission of light means you have to tell me what is the ether. What was the main... Now remember, if I show you the next slide, we believed this until the early 1900s. Okay? Newton's around about 1600 and something. So at the same time as René Descartes, a little bit later. Okay? Rightio, here's this magical stuff called the ether. This is the model of transmission of light. The ether's properties that we believed. Okay, unfortunately, it's a little bit Santa Clausy. The ether is universally present. Okay? It's everywhere. It's in you, it's in me, it's in the dog, it's in this room, it's in the middle of the sun. It's everywhere. It fills all matter. It permeates. Permeate means it soaks all the way through. It can pass through you unhindered. So it's not just in this room. If I walk, I would be walking through the ether. The ether would pass through me. Okay? This is the best one. It's totally undetectable. Okay, believe me, it exists, but you can't show it exists. You can't detect it. There is no way of detecting the ether. It was low density. It was so low density, there wasn't many particles of ether. They were so low, but it's still there. Okay? Because it's so low density, I can move and it can move through me and pass through me without much problem at all. Well, actually without any problem at all. The other thing is it's perfectly transparent. You can't detect it, you can't see it. Okay? We did believe in this, okay? And finally, even though it's so low density, so undetectable, so permeating, it's perfectly elastic. It's not like good old water. When you put something into water, a water wave goes on out. But after a while, the water wave starts to get smaller and smaller into a little ripple and then dissipates, doesn't it? That's because water's not perfectly elastic. When it moves up and down, a small bit of energy is lost because of friction with other water molecules. When I speak, my voice creates a compression wave, which eventually hits your eardrums. But people over in South Africa are not hearing my voice. So why? Because the air is not perfectly elastic, which means some energy is lost as the transmission goes on. But this magnificent stuff called ether is so perfectly elastic that light does not, once light starts, it keeps on going. It doesn't get any softer. So that's the reason why light can come from the sun to here, and it's the same light. It's perfect.
Basically, they gave it properties to explain things that they couldn't explain.
Exactly. The problem is it's a historical model, isn't it? They inherited this. No one ever thought about, well, you know, should we believe this? You know, we were coming to the point where we all were trying to understand the motion of gravity and so on. There was Tsiolkovsky. He was trying to say, okay, the theoretical ways of getting rockets into space, and we're starting on our verge into the 1900s. Yet we've still got this thing here, which was first proposed by the ancient Greeks. Yet, given a little bit of push along the way by some famous philosophers. Okay? Only because they knew no different. So that's how light was propagated. It was propagated by this magnificent thing called the ether. And isn't it brilliant? It must be the most fantastic thing in the world. So Mickelson and Morley, or Michaelson and Morley, two good old professors and physicists, set about saying, okay, this part here really has a problem that's totally undetectable. Let's detect it. If it exists, we've got to be able to show it exists. We can't, faith has no, faith has no realm in science. You can't believe something exists physically in science unless you can prove it here. So we can't just believe in atoms, we have to give it proof. Is that clear? So the same thing is going to happen. We're going to prove this stuff, things, just as much as we have to prove biology, evolution, and so on, all these things. So how are we going to do it? So they're going to come up with this very famous, extraordinarily famous experiment. An experiment to which one of them is going to get a Nobel Prize and the other one's going to get the Daly medal. So, don't worry. Rightio. Now, what's going to happen is the ether is perfectly still. That's another thing about the ether. Because it permeates all space, what's going to happen is as the Earth moves this way, the ether, which are all the particles over here, okay, remember the ether is very low density, so there's only a few particles of the ether which can't be detected. So as the Earth moves that way, what is the particles going to appear to do? The ether particles are all going to appear to move this way, aren't they? Are you okay with that? So let's pretend that the Earth does not move, but the Earth stays stationary, and I'll remove that. And instead, that the ether moves through the earth. Are we okay with that? That's no problem. We can all cope with this. This is actually what the actual basis of the word relativity. That I can assume the earth is stationary and the ether moves through it. Okay? Rightio. Now, if I was remember, what does the ether actually do? It supports what wave? Light. Okay. So, if I had a light wave, and I'll put the light wave in white, and I sent the light wave out here, that way, okay, and I bounced it off a mirror over here, and then it came back as a reflection, what would it do? What would be the, what could happen? Well, remember, this is like a river. Now, the river is flowing which way? It's flowing to the right. Okay. So I want you to imagine that here is our river. Okay. Remember, the river, the water of the river is simply the ether, and it's flowing downstream, so it's flowing this direction. And I want you to imagine that you swim. Let's get a swimmer. Okay, I'll put some pink, there you go. Person swimming, feet over there, hands and hands. Okay? Right here. Now, imagine you can swim at a certain velocity. Okay, and you can swim this way. Are you swimming upstream or downstream?
Upstream.
Upstream. So, because the river is going this way, just imagine you can do this in certain time t. Okay? Now, you've got to the point at the top of the river, you turn and you go back. When you swim downstream, you're swimming with the stream, aren't you? Well, it'll be quicker, won't it? Okay? So, I want you to imagine that this happens in a certain time, which we'll call capital T. So, you have to swim against the river on the way up, which is exhausting, but on the way back, you swim the journey is much less time. Are we okay with that? But overall, we're going to call this journey as capital T. I want you to imagine that you have a friend, and this friend is going to not swim up and down the river, but swim across the river, backwards and forwards, the same length of distance. So if you have to go 100 kilometres up and down, then this other fellow or woman is doing the same distance. Okay? Now, this person is not swimming against the tide, okay? They're swimming at the same velocity as you, so would they take less time or more time to do it? Well, you can do the calculations. I'm going to put you out of your misery. The time taken for your other friend is less. We'll say little t, okay? So little t is smaller than bigger t. Okay? So you might take an hour and 20 minutes to swim up and back, but your friend just takes an hour to go across and back, same distance. And the reason is, even though you're swimming with the tide going down, you're really struggling on the way up. Are we okay with that? Whereas this fellow, the purple person, has not getting affected by the river at all, really, because they're not swimming in the direction of the water, either against you or with it. So really, their speed hasn't changed. Are we okay with that? Rightio. So, now Mickelson and Morley understood this. So what they're going to do is they're going to create an apparatus which sends a beam of light this way, bounce it off, and a beam of light back. And they're going to find the time for that. They're also going to spend, at the same time, put a beam of light this way and a beam of light this way and measure the time for that. Making sure that the light paths are identical in length, but not well, we know that it won't be identical in time, won't we? Which colour will have a longer time, the white or the yellow tip? White, okay. So we need somehow to have a stopwatch which is good enough to measure the differences in time between the two paths. Okay? And we want to be able to say, okay, if we are moving, if the Earth is moving through the ether in this direction, which it is, according to Aristotle and René Descartes and Isaac Newton and Fresnel, then if we put a beam of light in the white direction, it should be a different time than the beam of light in the yellow direction. Are we okay with that? This is the basis of detection. And that's what Mickelson and Morley are going to create an experiment for. Are you okay with the idea? Right. Now that we've done it, now we've got the idea of how to detect the ether, this is what they actually did. Remember, we're talking about the Earth being still and the ether moving through us. So they use the word ether wind to feel that, you know, that the ether are moving through. Really, is the ether moving? No, the Earth is actually moving through the ether. And if the Earth is moving through the ether, but we think the Earth is still, then the ether would be feeling as if they're going through. They call that the ether wind, which is the same as the river going up or downstream. Okay? So when you swim with the wind, you get wind assisted. When you swim against the wind, you take a longer time. But still, the journey in the direction of the wind should be a longer time than the journey across the wind. So how do we make sure that the two paths are identical? And this is the way it's going to happen. So, we firstly start with a piece of light. Now this light over here, it can't be just any old light. It's got to be light of a single wavelength. And there's reasons that we've got to do that. It's called coherent light. Because light, as you know, spreads out. So the first thing they're going to do is they're going to make sure that it's coherent light, which is what we would now use would be a laser. Okay, a good laser. And you get a nice tight beam, collimated. So here's our light source. Okay. Very quickly, in the last, I'll talk the last century, the 1900s, the century before that, we had great mirrors, and mirrors have been around for ages. If you've ever travelled in France, the Hall of Mirrors in Versailles is beautiful and so on. There are mirror makers who are brilliant. And we have what we call half mirrors, mirrors that allow light to go one direction, but don't allow it to go the other. You've all seen that. We've got light that goes one way but reflects off the other surface. And they put one in the centre. And this one in the centre was at a 45-degree angle. So here is the light source over here. It bounced off here. Some of the light went through there, straight through, because a mirrored light, a semi-mirror or a half mirror, does allow some of the light to go through, but it splits the beam up to there. Okay? So the beam of light, some of it goes straight through, and some of it is bounced off at a 90-degree angle. 90 degrees. Why do 90 degrees? Because we want someone to swim with the river and someone to swim across the river, don't we? Okay? So, they're going to have this one. This is the one that's swimming with the river. There's the ether wind is coming this way. There's the upstream. Are we okay with that? So here, this beam there is swimming against the stream, and then it bounces back to here and then into a telescope. Okay? So that's the first beam path. Are we okay with that? So it's going one full way down, hits here, and swims halfway up the stream again, assisted with the ether wind. Okay? So that's like swimming down fully against the river and then halfway up and then measuring the time. The other one, the other pathway, hits the mirror, goes off this way and comes there. Are the two paths equal? Yes, they are. Okay? Rightio. So we've now got a person over here being able to detect or look at the two paths as they come back together in here. Are we okay with the setup? Rightio. Now, obviously, a single passage like that is not going to be good, is it? Single pathway, whatever. We need to, because light is travelling so fast, we need to be able to make these bounce backwards and forwards hundreds of times. So the reality is the paths, according to this one here, there's miles of mirrors. But in the HSC, when you're asked to do this, you just do a single bounce, okay? Don't do hundreds of bounces, just a single bounce, okay? So in reality, one pathway goes this way, hits a mirror, and then down like that. The other pathway, and I'll do it if the colour in blue, goes this way, hits that river, and comes back down here. Okay? The amount of times they go backwards and forwards is dependent upon other things here. And the other thing that they really want is, how do you time the speed of light? Okay, can we use a stopwatch? Is there ability to use a stopwatch to say, okay, let's time one path and then the other? Is that possible? No, no timing mechanism could be used. So how are we going to do it? And Mickelson and Morley come up with this great idea. They know that when two light beams come back together, they will interfere with each other, superimpose as we know it. So here are two water waves. And you can see if you put two things, you drop something into the river or into a ripple tank, and you just give it a nice little bit of a push, then the two ripples spread out, and they make this most magnificent pattern called an interference pattern. Okay? And if we make one go faster than the other, you get a certain interference pattern. So we know what will happen. Okay, so here we are. This is an interference pattern that the person will see as it comes back. Okay, are we okay? The person sitting here is going to see this stripy pattern. Okay, how's that? You okay with that? Rightio. Now that's the setup. Are we okay? Thumbs up? Good. Okay. This thing now is, okay, what are we going to do? They're now going to rotate this thing by 90 degrees. So this pathway, the blue pathway, no longer is going across river. It will now go with and backward with the ether wind. So what should happen to this little pattern over here? It should change, shouldn't it? As we turn this thing here, the two pathways, what should happen is we should see a change in the pattern and then it return to the same pattern again. So as we spin this thing around, we should see the stripe pattern change and then to something really weird and then come back to what it was. The reason being is we can't measure the time, we can measure how much the waves come in or out of phase. So what I mean by that is, remember, light is a wave like that. So when one of these waves comes here and the other wave is slightly out of phase because it's swimming upstream, they will interfere with each other and create a superposition wave, like two water waves coming together at different speed. Are we okay with that?
Yeah.
And this water pattern, obviously it's not water, it's a light pattern, will be the stripy lights. How's that? Because there's no possible way, is there, to measure the time. So as we turn this around, we should see this. So, now hopefully this is working. And there, and there, no, that's, no. Where is it? Come on. Just pause that.